So this is ELC111, Introduction to Electricity, and this presentation is on transistors. Now the correct name for this device is a bipolar junction transistor. However, almost everyone in the field just simply refers to these as transistors. Now there are different types of transistor devices, but these are field effect transistors, and they will not be discussed in this course or in this presentation. Now the transistor has three terminals: the collector, the base, and the emitter. And transistors come in two configurations as shown in figure 1. They are either NPN transistors or they are PNP transistors. So referring to figure 1, note with the NPN transistor, the collector terminal connects to N-type semiconductor material, the base connects to P-type semiconductor material, and the emitter connects to N-type semiconductor material. And of course, referring to figure 1, the PNP transistor is just the opposite. The collector is connected to P, the base to N, and the emitter to P-type semiconductor materials. Now the schematic symbols used for junction transistors are shown in figure 2. Note that the terminal with the arrow always denotes the emitter of the transistor, and the arrow always points towards the N-type material. This is how we can identify the three terminals on the schematic symbol and also determine whether the schematic symbol refers to or denotes an NPN or a PNP transistor. Now, transistors come in different case styles, and they can come either in what is called a surface mount device, SMD, or a through-hole device. The difference is that the surface mount devices are soldered only to one side of a printed circuit board, whereas the through-hole devices actually solder through or into a hole that goes through the printed circuit board from one side to the other. Now in figure 3 we see a transistor is called an SOT-23 case style. SOT stands for small outline transistor. And in figure 4 we can see the dimensions of these devices. The SC70-5 is approximately 2 millimeters by 2 millimeters, and the SOT-23-5 is 2.9 millimeters by 2.8 millimeters. Now the through-hole devices, as we see in figure 5, can come in many different case styles, and we see that with these transistors that some of them have a plastic case, and these are typically low power devices, and they can also come in metal cases, which are high power devices. The metal case is required to be able to dissipate the power that's generated inside the transistor to the surrounding air. Now, the primary metric or quantity that we use to discuss or describe a transistor is its forward current gain. Understand that the transistor is determined to be a current controlled device. And what this means is that the base current controls the collector current. The base current is the input and the collector current is the output. Current gain is symbolized with the Greek letter beta, and mathematically beta equals the collector current divided by the base current. For most transistors, beta can range from around 100 to around 300. Now this is not a precise number. Again, if we select a particular transistor, the manufacturer tells us that the beta value can range between these limits, and it's simply because they can only so closely control the amount of dopants that are added to the semiconductor material when they construct the transistors. And again, the doping levels determine our value of beta. Now, one of the most widely used applications for a transistor is just function as an amplifier. And what we do with an amplifier, we apply a small AC signal at the base, which causes a large AC signal at the collector. Again, the collector current will be anywhere from 100 to 300 times larger than the base current. And a good example of the use of an amplifier is to take a small AC signal from a microphone. This is typically in the millivolts, and with that create a larger AC signal at the output to send to a device like a speaker. Now we'll just look briefly at how and why a transistor operates like it does. Now, first of all, understand that we have to apply some voltages to the transistor in order to turn it on. So in figure 6, we see an NPN transistor, and we have 0.7 volts applied to between, or a 0.7 volt difference applied to the base and emitter. Now, the base to emitter acts just like a diode, with the base being the anode of a diode and the emitter being the cathode of the diode. And remember that when we apply 0.7 volts to a PN junction, the depletion region will become very narrow. So we see here a forward bias depletion region between the base and the emitter. And I'll write forward bias here, or FB for forward biased. So this base to emitter junction has to be forward biased in order for the transistor to turn on. Now note in figure 6, we've applied a voltage of 5 volts with positive on the collector and negative on the emitter. Now with this 5 volts applied from collector to emitter, understand that from the collector to the base, that we have a positive 4.3 volt difference from collector to base. So the collector with respect to the base is reverse biased, which makes this PN junction right here be reverse biased. And again, as illustrated in figure 6, this depletion region becomes very wide. Now, the operation of a transistor is really due to the fact that the emitter region is very heavily doped. In other words, there's a lot of free electrons in the emitter region. And the base region is very lightly doped, and it is physically very narrow or very thin. And the collector is moderately doped. Again, it's got a moderate amount of free electrons. And hopefully this is illustrated for us fairly well in figure 6. Now, when I apply this 0.7 volts from base to emitter, again, I can overcome the base to emitter depletion region and have electrons flow from the emitter into the base, as shown here. So we've got a lot of free electrons flowing through this depletion region. Now, in order for an electron to turn the corner and flow out of the base, it must fall into a hole. And because the base region is so very lightly doped that we have very few electrons turning the corner and flowing out the base lead. Most of these electrons continue to flow through to the collector region. And again, from our beta values, we know that this ratio is anywhere from 100 to 1 to 300 to 1. So for every 100 electrons that flow through this forward bias depletion region, only one of them turns the corner and goes through the base, or out the base lead or the base terminal. Now, when we talked about diodes, you were told that electrons just don't flow through a reverse bias junction. However, with the transistor's operation, this is a little bit different because these electrons are attracted to the positive potential that exists up here at the collector. So even though the base to collector junction is reverse biased, the majority of the electrons will continue on through the reverse bias junction and flow out the collector lead. So again, even though we have a lot of electrons flowing through the forward biased base to emitter junction, anywhere from 100 to 300 of the electrons that flow through there will continue on to the collector, and only one will turn the corner and go out the base lead. Now, in order for our transistor circuits to function, they have to be biased. And what this means is that we have to apply an external voltage that sets up the operating point of the transistor. So we see a simple transistor biasing circuit in figure 7. We have a source voltage of 12 volts. We have a base resistor of 1 megohm, and we have a collector resistor of 3.6 kiloohms. And the output of this transistor circuit is the collector with respect to ground. Now, our resistors, RB and RC, are called the biasing resistors, and those resistors, again, are used to set up the transistor's operating point. Now, the base resistor, RB, is what determines the base current. And note that whatever current flows through the resistor RB has to flow into the base of the transistor. It has no other path. So we can determine or calculate the base current as shown. The base current will equal the supply voltage minus the 0.7 volts that is dropped from base to emitter. Again, this is a forward biased PN junction, just like a diode. So from base to emitter, we're going to have a 0.7 volt drop as shown. Now the rest of the voltage Vs has to be dropped across the base resistor RB, and of course Ohm's law tells us that whatever voltage we have, the current through a resistor is the voltage across that resistor divided by that resistor's value. Now, from the previous slides, we were told that the collector current is amplified or multiplied times beta. So the collector current, the current that flows down through the collector, is going to be a multiple of the base current. And of course, when the current flows through the collector, whatever current flows through the collector resistor has to continue on through the collector. It has no other path. And when current flows through the collector resistor, this is my collector current, IC, that also flows through the resistor RC, that it's going to make some voltage drop across that resistor RC. So the output voltage will be equal to the supply voltage, 12 volts, minus the collector current times the value of the collector resistor. Well, let's analyze the circuit of figure 7. Let's put some numbers in here and do some calculations. So again, we're given that the base current equals the current through the resistor RB, and Ohm's law tells us that current equals VRB divided by RB. Again, with the transistor, we're going to drop 0.7 volts positive to negative from base to emitter. So the difference between 12 volts and 0.7 volts is dropped across the resistor RB. And so if we take 12 volts minus 0.7 volts divided by 1 megohm, that tells us that we have 11.3 microamps flowing into the base of the transistor. Again, I'll have 11.3 volts dropped here, and 11.3 volts divided by 1 megohm. Oops, I messed that up. Gives us 11.3 microamps. Now we know that the collector current equals beta times the base current. We're given a beta value of 145 for this transistor. So I know that the current that flows through RC and into the collector of the transistor, IC, equals beta times IB. So 145 times 11.3 microamps gives us 1.64 milliamps. Now, when 1.64 milliamps flows through the collector resistor RC, there'll be a voltage drop here of approximately 5.9 volts. And of course, 5.9 volts subtracted from 12 volts gives us a voltage difference from collector to emitter of 6.1 volts. So my output voltage with respect to ground will be 6.1 volt. Now, we look at figure 8, or in figure 8, we see an example of a transistor amplifier. Now, the purpose of an amplifier, again, is to take a small AC signal and turn that into a big AC signal. So looking at the circuit of figure 8, note that I have an input voltage of 20 millivolts at a frequency of 1 kilohertz. Now with my transistor amplifier, I have to have a way to allow that AC signal to pass to the base of the transistor, yet block the DC current IB from flowing back through the input voltage. And if we remember the plot that shows us the capacitive reactance, X sub C, as a function of frequency, remember that at low frequencies, X sub C is extremely high. But at high frequencies, X sub C gets very small. So the opposition to current for the 1 kilohertz signal to pass in this direction, that opposition to current is very small. However, the opposition to direct current flowing back in this direction is extremely high because 0 hertz is right here. So no DC current can pass to the left, but a large amount of AC current can flow from Vin through to the base of the transistor. and this component Cn is called a coupling capacitor. So what we're doing now with the amplifier is through this capacitor, we're able to add this 20 millivolt signal to the 0.7 volts that normally exists at the base. So we see if we were to look at the base voltage, then the base voltage is going to, where it would normally be here at 0.7 volts, this base voltage is going to increase and decrease and increase and decrease and increase and decrease. Therefore, my base current is going to be able to, of course, increase and decrease and increase and decrease and increase and decrease. This is the base current. And this will cause a much larger change in the collector current, because again, remember, the collector current is amplified times beta. And of course, the output will vary above and below the 6.1 volts excuse me, that we saw in the previous slide. So for this transistor amplifier circuit of figure 8, I ran this simulation in Multisim and plotted out captured and then plotted out the output voltage as shown in figure 9. So again, the input voltage was 40 millivolts peak to peak, 20 millivolts peak. And note, looking at figure 9, that our output voltage is 8.86 volts peak to peak. So my input voltage only has a 40 millivolt peak to peak swing, and the output voltage has an 8.86 volt peak to peak swing. Now, when we discuss and describe amplifiers, one of our key metrics is what's called the voltage gain. Gain is symbolized with the letter A, and the subscript V tells us this is a voltage gain. And mathematically, the voltage gain is simply V out over V in. So for the circuit of figure 8, our output voltage is 8.86 volts. Our input voltage is 40 millivolts. So this amplifier has a voltage gain of 222. And of course, and note that the voltage gain has no units, because mathematically it's volts divided by volts. It's simply a relationship or a ratio of the output with respect to the input. So notice with the simple amplifier circuit of figure 8, I can take a small AC signal, 40 millivolts, and change that or convert that to an AC signal with a peak-to-peak value of 8.86 volts. And again, in order to have an amplifier, we must have some DC voltage source to power the transistor. And of course, this DC voltage source is what creates the base current and the collector current to allow us to have amplification.